All right, now we're going to start talking about one of the most important theorems you'll see in circuit analysis, and that is Thevenin's theorem. So we're going to look today at what's called the Thevenin equivalent circuit and how to create it. So Thevenin equivalent circuit is based on Thevenin's theorem, and what is that theorem? Well, I'm not going to bother to actually go through and do the proof. You can actually find that in your textbook. But Thevenin's theorem basically says this. Given any linear circuit, which of course is what we are working on in this class, with two nodes A and B for that circuit, we can perform a transformation such that whatever is in this linear circuit can be reduced to a voltage source in series with a resistance, where Vth is our Thevenin equivalent voltage, Rth is our Thevenin equivalent resistance. And this in turn is our Thevenin equivalent circuit. So any circuit, any linear circuit with two terminals A and B that are pulled out of that linear circuit can be reduced to a voltage source in series with Rth, such that if I connect any load between A and B, I'll have the same voltage and the same current. So as far as anything I connect between the A and B terminals, both circuits will behave exactly the same. So any load connected between the A and B terminals will behave the same for both circuits. In other words, the voltage and current that I will measure will be exactly the same. So looking at this, this is actually very, very similar to what we were talking about before with source transformation, when we were taking a more complex circuit and making it simpler. We were reducing the circuit. Thevenin's theorem is simply a broader definition or broader technique for this type of simplification that works for any linear circuit, not just circuits that have independent sources and resistors. So we're going to learn how to apply Thevenin's theorem, and this in fact turns out to be an extremely important theorem. You see this used all the time in the analysis of real-world circuits, for example, transistor amplifiers. So this is a very important technique, and we will in fact practice it and see it quite a bit in this class. Okay? So, given this introduction for Thevenin's theorem, how do we go from here to here? What is that transformation? Well, let's go through that technique and then let's work some examples. So how do we find Vth and Rth given a linear circuit? Well, let's say we have a circuit. We have nodes A and B. and I want to perform a transformation into a Thevenin equivalent circuit. And let's say, just for the sake of argument, there is some kind of load connected between terminals A and B. And this can be a resistor, or it can be a network of elements connected together, another source, multiple resistors, anything. So let's just assume there's something connected between A and B. So I want to do this transformation. The first step is remove the load. So if there is a load connected to your circuit, you must disconnect that load before you apply Thevenin's theorem. Once you do that, you just calculate what's called the open circuit voltage between A and B. And this is open circuit as in no load connected to it. So for my VTH calculation, find VOC, the open circuit voltage, i.e. no load. I calculate VOC, and I can do that using any circuit technique I want, mesh analysis or nodal analysis, any way I want to do it. Once I find VOC, VTH is simply equal to the open circuit voltage. It's as simple as that. So that's how we find VTH. Now, how do we find RTH? For my Thevenin resistance calculation, I take this circuit and I set any independent sources in it to 0. Set all independent, not dependent, independent sources in the circuit to 0. So in this case, I have a linear circuit with the independent sources set to 0. And what do I mean by that when I say set to 0? What that means is if I have a voltage source and I set it to 0, it becomes a wire. If I have a current source and I set it to 0, it becomes an open circuit. So this is no different than what we saw before when we looked at superposition. Okay, once you do that, I calculate the equivalent resistance between A and B. And once you do that and you calculate that equivalent resistance, then RTH is just equal to that equivalent resistance. And that's how you find Thevenin's theorem. Conceptually, very straightforward. Let's work an example and see how this works out in practice. So let's find the Thevenin equivalent circuit for this. All right, I want to find the Thevenin equivalent circuit between A and B. There's no kind of load connected, so it's already in an open circuit condition here. And I now want to go through and find the Thevenin equivalent. Now, looking at this, you might recognize that you could probably reduce this circuit using source transformation and element reduction like we did last time. And you could do it that way, but Thevenin's theorem is a far more elegant way of accomplishing the same goal. So let's go through. Let's first find Vth. So we find the open circuit voltage. I'm going to find the open circuit voltage between terminals A and B. I can use any technique I want. In this case, I'm going to use nodal analysis. I'm going to ground the bottom node. And notice if I ground the B node, then the voltage here at the A node, it must be a nodal voltage of VOC because of the way I'm defining the voltage drop. So VOC minus 0 is equal to VOC. So in this case, I've got VOC. Now looking at this, this is an open circuit. There's nothing connected to the other side of that 4 ohm resistor. So looking at this, I can do a quick kind of inspection definition here. If there's no current flowing through the 4 ohm resistor, that means there's no voltage drop across the 4 ohm resistor. So if I have VOC on this side, what must be the voltage on this side? It's got to be VOC. So in this case, just because I know there's no current through the resistor, I know that I must have the same voltage on both sides of that resistor. Okay, so this node is actually VOC. And now I can go through and I can write my KCL equations. So in this case, I'll draw my currents. And I can write my KCL. This is 25 volts. That node is defined. And what I'll have is that 3 amps going in for the VOC node must be equal to VOC over 20 plus VOC minus 25 over 5. One equation, one unknown. I solve it, and what I will get is that VOC is equal to 32 volts, which is therefore equal to my Thevenin equivalent voltage. So it's just that simple. I could have also, of course, solved this with mesh analysis as well, but I just preferred nodal analysis. Okay, now let's find the Thevenin equivalent resistance. Let's go back to the original circuit, and now let's zero out all of the independent sources. That voltage source becomes a wire, that current source becomes an open circuit, and I wind up with this circuit. Now I need to know what the equivalent resistance is between the A and the B terminals. And in this case, it's pretty straightforward. Clearly, the 5 ohm and the 20 ohm resistors are in parallel, connected together on that end, connected together on that end. So if they're in parallel, what I have is 5 in parallel with 20 is equal to 5 times 20 over 5 plus 20 is equal to 4 ohms. So this is 4 ohms, and I've got 4 ohms in series now with 4 ohms once I go through and reduce these two resistors to 1. So I'll get rid of that. I'll make that into a 4 ohm resistor. And so now I've got 4 plus 4, and therefore Req is equal to 8 ohms. And therefore RTH is equal to 8 ohms. And there's my answer. That is my Thevenin equivalent circuit. My Thevenin equivalent circuit is composed of a 32 volt source in series with an 8 ohm resistor. So that is our Thevenin equivalent theorem applied to a linear circuit in a nutshell. Now, when I started this off, I said, if you create a Thevenin equivalent circuit, anything I connect between A and B for the original circuit or the Thevenin equivalent circuit will behave the same. Okay, let's test that. Let's say if that's real. Let's find out if that's real. Let's take this circuit here, my Thevenin equivalent, and let's connect something to it. In this case, let's connect a load resistor, 8 ohms. And let's calculate the V load voltage across that load resistor. Well, in this case, this is pretty straightforward. I've got 32 volts, 8 plus 8 is 16, so the current flowing around this loop by Ohm's law must be equal to 32 divided by 16 is equal to 2 amps. And therefore, V load must be equal to 2 times 8 is equal to 16 volts. And of course, I could have done this with voltage division or nodal analysis. I could have solved this any way, any one of several different ways. Okay, if this is true, if these are equivalent circuits, let's go over here. Let's take our original circuit and let's check to see if this is truly an equivalent circuit. Okay, so starting off with the original circuit, I'm going to once again attach an 8 ohm load resistor to it. And once again, I want to calculate V load across that load resistor. Since I do like to use nodal analysis, I'm going to keep the B node grounded here. And by definition, this now becomes V load. Now, question is, do I have V load on the other side of that 4 ohm resistor? Nope. Because now I've got a path for current to flow. So now a non-zero current flows through that 4 ohm resistor, which means I'll have a voltage drop. So I don't know what the voltage is on the other side. I'm just going to go ahead and call this V1 for this node here. And now let's go through and let's do our calculations. Okay, now here's a case where the V load node is a non-essential node. But since I want to calculate V load, I'm going to go ahead and write a KCL equation for it. So here's one of the situations where you do want to actually write a KCL equation just because you need that value anyway. So I'll pick these directions, okay. In fact, since I've already got V load defined, then the direction of the current through that 8 ohm resistor is already defined. And then I'm going to pick this same current, they're in series, same direction. And over here, I'll once again do exactly what I did before, pick the same directions, and once again, that's 25 volts. Now I can go through and write my KCL equations. And so, in this case, for my V1 node, I've got V1 minus 25 over 5 going out, plus V1 over 20 going out plus V1 minus V load over 4 going out must be equal to 3 amps going in. So that's my KCL equation for V1. For the V load node, in this case, 4 minus V load over 4, or pardon me, I should say V1 minus V load over 4, excuse me, must be equal to V load over 8. And I solve. And if I solve these, guess what V load is equal to? Well, hopefully it won't surprise you that if these are solved, V load is equal to 16 volts. In other words, I get exactly the same answer as I did with the Thevenin equivalent circuit. So this is a valid transformation for that original circuit. And I could connect anything between terminals A and B. Any value resistor, I could connect another source. I could connect another circuit across A and B with multiple elements. Doesn't matter. I'll see the same voltage between nodes A and B regardless of what that circuit is. So I'll get to see the same voltage here as I saw here. These two circuits are equivalent to each other. Okay? So that is Thevenin's equivalent in a nutshell. It is a way of taking a complex circuit, distilling it down such that anything I connect between the A and the B terminals, I'll see the same voltage in the original circuit as I do in the equivalent circuit. Very useful transformation, and as I said, used a great deal in transistor circuits. Okay, so just to emphasize, the load can be a resistor. It can be a source. And it can be any combination of sources and resistors. So any combination of circuit elements. So you'll see most of these circuits will use a resistor just when you're working a problem, but really it can be anything. And you will still see for the Thevenin circuit, as you did for the original circuit, you'll still see the same voltage between the two of them, or the same current flowing into them either way. Okay? All right, that's Thevenin's equivalent. Pretty straightforward example, but you may note here that in this case, there were no dependent sources here. There were just resistors and independent sources. What if I had a dependent source in that circuit? How would Thevenin's equivalent change? How would Thevenin's theorem have to be applied? Well, next time we'll look at that. We'll look at a Thevenin equivalent transformation that has a circuit with a dependent source, and we'll see how we need to modify these techniques.